Welcome back to the class to both of you, Ms. Patricia and Mr. Marco. We will start our today lectures. Basically, in the last five lectures, um, I have teach you regarding the risk assessment process through the IC standard 62305-2. But today, basically, the risk assessment which I have performed in the classes is regarding the our project, which is 620 megawatt uh, large scale project. So I have selected the overall area of that project, and this risk assessment is not satisfying. So the process for that, we have to divide that area into different zones, like small chunks there, and we will perform the risk assessment for that area. Also, another option is that we will perform the risk assessment for the number of different heights available in that area. The PV module structure height is less than 5 meter. Like this type of working we will perform. But this project is in actually in the starting of the design stage. So when I will perform this risk assessment after couple of months, I will share this report with all of you, both of you, to read out and see what happened there. But because the purpose of that risk assessment to perform in the live class, because in that risk assessment there are the all other points are available there, like transmission line, heritage, everything is present there. So the risk in that area is much higher than the other options. So when I will get the updations in that area, like the risk assessment, I will sharing in the group for your knowledge, both of you. And another point, uh, yesterday our company has hired the experienced company, like Dan company, which is in the South Africa, most powerful in the lightning protection study. And where we are currently, we are installing our solar power plant in this is in the mines area. We have performed the risk assessment as per IC standard, but as the client has required that, we will involve the Dahan company for their review of the risk assessment. So our company has involved for the review of the risk assessment to Dahan company, and hopefully we will get the updation from that company. And also I will share with both of you in the group this update, uh, how much we need to change uh, in the risk assessment, what are the updation in the risk assessment as per the experience guide, uh, other than me, because I'm uh, in this field like 2 to 3 projects. But this company is very experienced company, so I will share the updation to both of you for your knowledge. Okay, for the today working, the lecture is regarding the lighting protection design. Basically, when the our risk assessment is not satisfied without the lighting protection, then we need to give the lighting protection for that purpose. So for that calculation, we need to apply the classes of the LPS protection through the rolling sphere method in the PV area. So when we will perform this risk assessment as per the IC standard and perform the lighting protection as per IC standard 62305-2, we need to give the to roll our rolling sphere on the PV area. Check whether whether the the discharge area or the safe area which is under the rolling sphere. How much distance, how much the of the distance of the height of the lighting protection like the finial is required. So for that we are performing this uh, protection designed for 2 day lectures. So now I'm sharing my screen and we will discuss our lectures. So basically as per the IC standard 62305 dash 1, they give us the lighting levels, lighting protection levels, level 1, level 2, level 3 and level 4 classes. And also they give us the options of the rolling the other method like the protection angle method, rolling sphere and the mesh. Basically the I have explained in the previous lecture that the mesh method is basically used for the earthing purpose. The protection angle method will be like the in the substation in that area it will be used, but in the PV area the rolling sphere method will be used. So that is why they give us the option of the rolling the radius of the rolling sphere should be 20, 30, 45, and 60. For the level 1 protection is 20, level 2 is 30, level 3 for the 45, and level 4 is 60 meter radius. And same is the earthing mesh they have given option. But this earthing mesh is basically used for the substation area or the small area. We will use this sizes like the 20 by 20, 15 by 50, 10 by 10 by 5 by 5. But in the PV area, the area is too large. And we will, when we will apply this 20 by 20 sizes in the PV area, the lightning, uh, the conductor quantity is too much higher size. And this, they will increase the cost of the overall project because it is a copper conductor or aluminum conductor, any other options which is satisfying the our earthing calculation. But the quantity will increase, the cost will increase, and they will affect the overall cost of the projects. So the optimal solution is that we will we will draw the layout as per the 50 by 50, 100 by 100 meters spacing between the conductors, vertical and horizontal. If I will mark that this one, like this one. Now it will be this will be 20 and also the horizontal. Now this will be 20 and this will be 20. So mean that 20 by 20 box we will make. Like here is the overall area. Like we will assume that. And if we apply like 20 by 20, like this, like this, like this. Now you can see that This 20 by 20 is too much on higher side. They will increase our the cost of the solar project. So what is the optimal position is that we will do make the layout, make the layout like that. I will mark that there. Like it is our solar project, and we will like that. One is vertical, horizontally like the PV module area, like that. Now, like this is the earthing mesh we have connected. Mesh means that they are connecting with each other, basically in the loop area. Like you can see that they are connected with each other and they are in the loop phase. Now we will do the simulation on the different software used in the industry. One is the LGS, uh, and the other one is the CDEC software will be used. The third one is the ETAB. ETAB is basically used for the small project sizes, but mostly CDEC is software is used for the underground earthing. The LGS software, which is option for the overground earthing. Some of the area where we can't do the excavation of the due to the different reasons, like in that mines area. In the mines area, the client will not accept the excavation of the solar sites. So what is the process that we have to do the everything over the ground, like the earthing, the foundations, everything should be in the overground area. So now the option is totally we will run the conductor in the trays or any other options, and then we will just do the holes, bore holes there in the PV area, and we will just close that holes. So these software will be used to do the earthing calculations, and when we use these software, we will get the optimal options of that. Like this type of option, the spacing we will increase between the conductors, and this will when we will get the optimal step and touch voltages uh, in the limited, yeah, tolerable limit, ground resistance in the tolerable limits. So when the software is satisfied in that area, we will submit that earthing calculation to the client that in it is okay. Now, our main topic basically is not the earthing. Our main topic is the rolling sphere method. So basically, they give us that options. When we will use the class one level of the protections, they will basically increase the lighting protections quantity. The conductors, when we are using the lighting protection there in the PV field, we have to connect to the conductor to the main earthing mesh. Like if we like draw, I think when I like there, you can say that when these are the solar panels, one is earthing there, one is there, one is there. So when this earthing is connected, we have to connect this conductor with the main earthing mesh. So the main purpose is that we have to connect our lighting protections to the main earthing mesh there. I will show you in the drawing. Uh, so the if we increase the number of the lighting protection class, if we satisfy the level 1 class or level 2 class, this will increase our cost of the solar projects, because in the substation area, in the small area where we are doing the earthing calculation or lighting protection study, there might be chances that the area is too small and we will get the optimal solution. But in the solar field, the area is too large. And if we use like the level 1 protection, this type of we will use in our calculation, this will increase the overall solar project cost and will affect the overall project profit to the companies. So the companies will like they are hope that we will give the optimal solution to the companies and they will get the optimal results. Neither they will in the EPC company will be in the loss, and neither the system is unprotected. So the designer have the right to do the basic earthing calculation, basic risk assessment, protection design. They are in the optimal solutions, not too much on the lower side and not too on the higher side. So this is the main purpose of that calculation. So if we use the level 4 protection, this is basically now I go to the now you can see that I have just draw the lighting finials. Like this is the lighting finial, this is lighting finial, this is lighting finial, this is lighting finial, this is lighting finial. Now our purpose is that I will like I am using the class 1. So level 1 protection mean that the radius will be 60 meter. So this is the 60-meter height. Now what I will do, I just copy this, move that, and to rotate this circle to connect. So now you can see that uh, this rolling sphere is basically touching to the PV modules. So this area, like I will mark that this area, this area, these are basically the area. Like I will take the screenshot. Like I want to say that like this is the area which is protected. But in that area, you can see that the Rolex sphere is touching to the PV module. So in that area, there might be chances that it will be the strike to the PV module and damage the PV module. This area is okay. Um, Basically, under the rolling sphere, the area is called that the protected area. But over the rolling sphere area is not protected, and the strike options available in that area. So now the other option is that now we have to give the distance, uh, do the less distance. Now I move that rolling sphere to this option. So now you can check that. You can check that this rolling sphere is over the PV modules. There is a gap between the uh, PV modules and the rolling sphere. Like this, you can see that it is around zero point 0.9 meter, 0.09 or zero point 0.1 meter spacing between the rolling sphere and the mounting PV module. So you can see that this is basically, I will go there above and explain another options. This is like, so basically, this is called the termination conductor or the termination rod, and this is basically this one. You can see that the screen, green one is the basically the rolling sphere. These are the two rods, are the lightning protection black one. This one is a basically, this one basically rod. This one rod. This is basically the rolling sphere, uh, rolling sphere area. So this one, you can see that this is called the distance, like the top of the lighting protections to the depth of the rolling sphere. It is called the penetration depth. Basically, the penetration depth, and this is called this from the lower edge of the rolling sphere to the top of um, the equipment which we are having to save that. This is basically called the safest distance, or the distance between that. It is called the safe distance. Separation distance between the air termination finial and meters. So basically, the separation distance is this one. This is between the two finials. It is called the separation distance. This is basically called the penetration depth. Distance between the two finials is called the separation distance. It is the height of the it is height of the finial, and now we have to calculate like the design of the lighting protection of mounting structures, separation distance from the, so like here is the calculation. I have calculated that for the 1 meter height of this is basically the 1 meter. This is basically the 1 meter height of the lighting finials, and the maximum separation distance between the air terminal finials of the PV module. So basically, when we are checking the lighting protections, we have to check in the horizontal plane and also in the vertical plane. Now it is the vertical plane. This one is the vertical plane, and I have to check that option also. Like 60, move, rotate. This is basically the 2D drawings, and they are not moving in the 3Ds. When we are doing on the SketchUp, or we do to the side view of that, and like orbit, like you can see that in when we are doing basically these are the 2D drawings. That is why they are showing that. So we have to check that options. And I have that checked that this 20-meter spacing between because it is the 10-meter pitch like center to center and 10 meters center to center. So the from that edge to that edge is 20 meters, and I have calculated that separation distance. The safest distance is the formula is that 2 into 2 RH. R basically the radius of the protections angle, like the sphere. H is the height of the finials, like 1 meter, minus H2. H2 basically the height. D distance between the air meters. D. So here we have calculated that if the 1 meter of the finial, the 20.81 21.8 meter is the distance between the two lighting protection finials is available, then our calculation, our rolling sphere will protect the overall area under that rolling sphere. So between the two finials, 20.8 meter is okay. But in our case, our distance between the two uh, finials is 20 meter, highest distance. We have to check that highest distance. So in the below calculation, I have calculated the separation penetration depth. Penetration depth formula is P is equal to R radius minus R square minus D by 2 square. D is the separation distance between rod and the two terminal is this one. Now, when I have put this options 20.81 meter, then the penetration depth will be 1 meter. So this distance is 1 meter penetration depth. Now we are calculating for our calculation, our system. So our system has 20 meter, the maximum separation distance between. So the penetration depth, when we are calculating that, our penetration depth will be 0.85 meter when we have calculated that option. Now we have to check the safest distance. Basically, the safest distance, this one available. I have the put that screenshot of the SketchUp file. Basically, the SketchUp safest distance safety gap is that air termination finial height minus the penetration depth plus the height of the structure between two air termination finials. So the height basically is lower than the penetration depth. So that's why it will be put 0. If this is the higher than the height of the structure between the two to the air termination finials. So the safest distance safety gap is between 1 air termination finial height minus 0.85 the penetration depth. So the remaining 0.15 is the safety gap. This is the safety gap available, which I have mentioned. This one. This one is when we are checking in that area, the safety gap is 0.15 meter, which is basically the calculation. I will share this file in the group. You will check again, and if you have any question, you can ask me in the group or in the tomorrow class. Now we will move on to the our MV station. When basically we have to protect our overall PV area, overall PV area. But in that area, like the PV area, we don't have any option that we will connect. Like here, we have installed the finials on the mounting structure. Like in that area, no PV module is there. So here is a no lighting protection available. So what we have to do, we have to give the lighting protection around the MV stations to protect the overall area. So for that, basically the height is around 5 to 5 meter, I think. No, I think it's 4 meter. I think it's height, and I have given the 5 meter rod plus lighting protection. This is basically basically it is just like pipe there, and on the top of the pipe we have installed the 1 meter finials here. So we have calculated that option also. The distance between the two lighting rods is 16.37. The height is 5 meter. Now what I have done that I have do the penetration depth. I have calculated that option, and we get the penetration depth is 1.13 meter. This penetration depth basically this one is the penetration depth. This one. So it when I calculated that penetration depth, it will be 1.13 meter. And now we have calculated the this safety gap. When I now you can check that basically this is the height of the our structure. Penetration depth plus the MV station height, including the concrete foundations. Because in the in that area, in that area, when we have installed the lighting finials on the mounting structure, the PV modules are under that, and our finial is above the mounting structures. But in the case of the MV stations, finial will be installed on the ground, and the MV station is in between the finials. So that is why we have considered the distance, the air termination height, and the penetration depth plus the MV station height, including the concrete foundation. When you can see that above this one, the height of the structure between two, this one is two air termination finials. So the mounting structure is in between that option. But in case of the mounting structure where for the PV modules, it is under the finials, not in between the. So that's why we have considered the zero height. When I have calculated that, we get that 0.854 is the safety gap, and our safety gap is basically higher than that. We have to check in the horizontal plane and also with the other in the mounting structure finials there. We have to roll over rolling sphere for the mounting structure, because it will be down to the ground. So we have to check with the ground also. That like I will mark that in the AutoCAD. I will show you like this one, and also move. Same like that. Copy we will like there is the ground available. So when we trim that options, it will be like that. They will be touched to the ground. One at the end of the mountain straight, it will be touched to the ground. This one, we have to give the lighting finials protections. So we have to check in the all the sides, not from the above side. We have to check from the other way. Like when I erase that option, like we have to check in that area, and also in the same in that area. We have to check from the all over the sides. Like we have checked that option is in that. We have to check in that area, and in also in that area. So you can see that we have checked in that area, and our administration is protected under the lighting finials. So this is basically the lighting finials calculations, and I have explained all the point there. And the other one is the option is that the conductor size. Basically, the conductor size which is used to carry out the current to the mesh if the light is present, lighting strike is present in that area. Now there are the multiple options that like the finials which are installed on the mounting structure. The IC standard 62561, which give us the option the lighting finials uh, IC 62561, which this IC standard give us the option that if our structure, the mounting structure, have the cross sectional area of 50 centimeter, 50 meter square, the the thickness of the mounting structure is 2.5 mm. The electrical conductivity of structure is like the 15th, I think they have given in the tables. If they have the specification of the mounting structure, these specifications, then we can use the mounting structure piles, mounting structure piles. I'm talking about the piles to the path of the lighting to the mounting to the earthing mesh. Like our this is the structure piles. This is the earthing mesh which is passing through that area, and we are connecting already our piles to the earthing mesh through the conductors, different conductors. And this pile has if if this pile has the specifications as per IC standard, we can use this pile as a path to the lightning current. But if the specification is not as per the IC standard, we have to use like here is the our finial is connected. We have to connect the conductor directly conductor and connect to the earthing mesh. we can't use this pile as a path. But if the pile has different options, like here is the rafter and pile, and this is the our finial. And if rafter or pile is the specification is as per the IC standard, then we can use as a current path. In our project, which mm, mm, which project I am currently working on that, in which we have connected contact to our vendor of the mounting structure, and we give the specification of the mounting structure, that the cross sectional area of the pile is this one, the thickness is this one, and then they have quoted our price, and we have used this pile as a direct path of the lightning protection. But if these specification is not as per the IC standard, we have to give the path or the conductor connect with the mounting structure. And we, if the specification is not as per the IC standard, we can't connect or mount the lighting finials on the mounting structures. So for the but the lightning finial which is installed on the MV stations, like this one, we have to connect the conductor to the earthing mesh, and we have to calculate the size of the this conductor as per IEEE 80 standard. They have given us the formula IKF under root TC divided by 1.9737. This is the formula they have given. I is basically the fault current. In our case, basically the fault current is out from the substation area, like in that area. It is 16 kmp. KF is basically the tables value from the IC, like IEEE 80, 11.74, 11.78 for the copper, and for the aluminium or the GI, different conductor use their the KF value is different. TEC basically the clearance time of the grounding fault in second. In our case, the grounding time is 0.7, 0.1 second. So when I put these values and I get the cross sectional area of 30.01. So near that this size, we have the 35 square conductor. So we have used that in our protections. So for the internal lighting protection systems, like the surge protection devices, we have to give that. These surge protection devices basically given by uh, the manufacturer, like the inverter manufacturer, give us the type 2 DC protection device SPDs. Like inverter also there, MV station type 1 and 2 their options. But if we don't have, we have to calculate the short circuit current, and as per the short circuit current we select uh, the SPDs type 1, type 2, type 3, that option. So basically these are the our calculations, and I have tried to explain every point of in that calculation and in the protection design. If you have any questions, you can ask me in the class today, or you want to ask in the group, or you want any help, I am available there. So on the Monday, our it is our last class, and I will recall other formulas from the previous one which we have discussed in the previous lectures, because this lighting risk assessment is very tough study, and it is very crucial study. and I will recall all other formula. If you have any question and any other points, you can ask me in that class.
Okay, thank you.
Yes, Miss Patterson.
Okay. Thank you, Mr. Aziz, for the class. Is it possible to share the notes you are using so that maybe
Yes,
I
yes,
can go through them?
yes, yes. I will.
Okay, kindly.
Yes, I will share. No issue.
Yeah, I think maybe once I go through them, I will post my questions in the WhatsApp group.
Okay, okay. No issue. No issue. Kindly, one request to all to both of you, because I am sharing the notes in the groups, and there might be chances that the some uh, like the data from our company, like project name or any other things. So kindly don't share with any other person.
Okay, for me that's in order. I've not been sharing.
Okay. Okay. Okay, Miss Patricia, if you want to continue the class, basically Mr. Marco has some issue in the PV system, and we have to discuss this in that class. If you want to join that, or if you want to leave, it's up to you. Mr. Marco, kindly share your screen and show me the issue.
Okay.